According to the World Health Organization, we are in a global obesity crisis. Worldwide, at least 2.8 million people die each year as a result of being overweight or obese because it causes a lot of health problems. Research concludes that 90% of the population consumes an energy excess. To reduce this positive energy balance, the energy intake should be decreased and the energy use should be increased. The energy intake is affected by the calorie intake by food consumption. The energy use is influenced by the resting metabolism, activity, and exercise. But what else can we do to increase the energy use? Maybe peppers can help to increase the energy use. Peppers contain capsaicin, which is responsible for the hot and spicy flavor. Capsaicin and several related molecules are known by the collective name capsaicinoids. They are produced by all plants of the genus Capsium. The natural occurring content of capsaicinoids differs in different kinds of peppers. It is shown that capsaicin activates the sympathetic nervous system, which causes suppression of hunger and hence satiety and stimulation of energy expenditure. Capsaicin is thought to activate the sympathetic nerves via specific receptors by stimulating the release of norepinephrine into the synaptic cleft, where it interacts with the adrenergic receptor. The aim of this study is to investigate if eating red chili peppers affects the fat oxidation in the body while at rest.
Let's meet the participants. The participants A and B are both obtained from the study Health Sciences at Maastricht University. They are both female and have approximately the same age, length, and weight. They will be fasting for 4.5 hours before the experiment will take place. Also, they are refrained from alcohol and sports on the day of the experiment, and the things we needed for the experiment are 2 times 200 milliliters of whole milk, 6.84 grams of chili pepper, and an indirect calorimetry. Participants will both lay on the bed. After 10 minutes, stable readings are reached. First, the baseline is measured for 30 minutes. After the baseline measurement, the participants will be provided with the intervention, which takes about 5 minutes. The post-measurement will take place for 60 minutes. During the measurements, the participants cannot talk or move.
During the intervention, participant A will drink a glass of whole milk. Participant B will also drink a glass of whole milk. Next to that, participant B eats 6.84 grams of red chili pepper. They have to consume this in a maximum of 5 minutes. During metabolism, basic macronutrients in food like carbohydrates, fats, and proteins are fuel for energy. These macronutrients are catabolized for energy in the presence of inspired oxygen and converted into carbon dioxide, water, and heat, a metabolic process known as substrate oxidation. In this experiment, we make use of this metabolic process by using indirect calorimetry for the measurements. Indirect calorimetry measures O2 consumption and CO2 production of a breathing subject. The O2 and CO2 output varies depending on the composition of macronutrients. Therefore, by determining the O2 and CO2 output, information about the type and rate of substrate oxidation within the body can be obtained. Let's talk about the O2 first. When looking at participant A, the O2 before the intervention remains approximately the same as the O2 after the intervention. When looking at participant B, the O2 increased after the intervention. So the O2 of participant A remains approximately the same. You can see that in the t-test table because the average O2 per milliliter before the intervention is 119.63 and the average O2 per milliliter after the intervention is 119.50. The average O2 of participant B increases with approximately 12 milliliters per minute. You can see that in a t-test table because the average O2 per milliliter before the intervention is 211.71 and the average O2 per milliliter after the intervention is 233.37. Next is CO2. When looking at participant A, the CO2 decreases after the intervention. When looking at participant B, the CO2 increases after the intervention. CO2 of participant A decreases after the intervention with approximately 5 milliliters per minute. You can see that in the T-table test because the average CO2 per milliliter before the intervention is 147.24 and the average CO2 per milliliter after the intervention is 196.59. Average CO2 of participant B increases with approximately 6 milliliter per minute. You can see that in the t-test table because the average CO2 per milliliter before the intervention is 168.86 and the average CO2 per milliliter after the intervention is 174.75.
The results suggest that there is a statistically relevant increase in CO2 milliliters per minute and O2 milliliters per minute in participant B, who consumed the pepper, while participant A, the control, had remained stable regarding O2 and showed a decrease in CO2. It is to be noted how without the pepper the standard deviations have gone down, although the average is being similar. This proves that eating red peppers will increase metabolism and oxidation through the fast-knit breeding results. Thus, burning more calories in that period as the citric acid cycle is more prevalent. This also suggests that there may indeed be a link between norepinephrine release and the energy expenditure post-pepper ingestion.
So the conclusion of this experiment is eating red chili peppers positively affects the fat oxidation in the body while at rest. There are a few discussion points about this experiment. One of the two instruments was not calibrated well during the experiment, causing some invalid negative values from participant A. When doing this experiment again, make sure the devices are calibrated. Next to that, we could have let the participants drink milk before the baseline measurement and after 30 minutes, so the only changed value would be the pepper. Also, to make this experiment more valid, we should have measured more people to get more results.